This is Mr. Potter. In our previous two lessons, we've been talking about the idea of parametric equations, where we have x and y being dependent on some other variable, some other independent variable t. And one of the things that we noticed is a great similarity between trying to find the magnitude and direction of a vector and what we recognize from our pre-calc classes when we're dealing with polar functions and polar coordinates. So I want to take some time to talk about polar expressions. So I want to do a real quick recap. In algebra, we usually talk about a particular point by its x coordinate and its y coordinate. So this point here is 3 units in the x direction, 3 units in the positive y direction. So we would call this point 3, 3. When we're dealing with polar coordinates, though, we're talking about the distance that we go from the origin or from the pole, and along with some angle from the positive x-axis. So this angle we can determine because this does make a right triangle with legs 3 and 3. And we saw in our discussion from vectors that theta is the arctangent of my y coordinate divided by my x coordinates. So when I'm talking the arctan of 1, that's going to be pi over 4. And if I wanted to determine the radius, this really is the same as the magnitude of the vectors that we were talking about last time. So this is the square root of x squared plus y squared. So for us, it's square root of 3 squared plus 3 squared, which is radical 18, which is 3 radical 2. And so in polar coordinates, I could call this the point 3 3 radical 2 comma pi over 4. So we're talking about our r coordinate coming first and our theta coordinate coming last, even though this theta is our independent variable, and we're used to seeing our independent variable come first when we deal with ordered pairs. R is really dependent on theta. So this is really a function of theta. Now, I've got this point listed here, but one of the things that we also discussed in our pre-calc classes was something called coterminal angles. The thing is, I could go from the positive x-axis to this line and get pi over 4 as my angle. But I also could make a full revolution before I come back here. So I could call this point 3 radical 2 and 9 pi over 4. I could also go counterclockwise from this, go from the positive x-axis, but go counterclockwise to here, and end up with a point 3 radical 2 and negative 7 pi over 4. All of these angles are coterminal with each other, and so all of these refer to the same point because of the periodicity of our sine and our cosine coordinates. But there is something else that I could do. I could, thinking about getting to this point over here, actually take an angle that's 5 pi over 4. In other words, somewhere on this line. But instead of traveling out from the origin, out from the pole, I actually want to take steps backwards. And taking steps backwards, in other words, going negative 3 root 2 at this 5 pi over 4 direction would give me the exact same point. So I actually have an infinite number of points. I mean, an infinite number of ways to represent a single point in polar coordinates. So that's something that's really important to know. So if I'm dealing with, say, the point 6 comma 6 root 3, then if I wanted to find theta is going to have to be the arctangent of 6 root 3 over 6, which would be the arctan of radical 3, and that happens at pi over 3, with my radius being the square root of 6 squared plus the quantity 6 radical 3 squared. And this comes out to be 12. So this point in polar coordinates would be the point 12 comma pi over 3. But in that same vein, I could also work backwards. If I had an r and a theta that were, say, 4 and 3 pi over 4, I could use that same idea that we had back in our vector discussion, where x is equal to r times the cosine of theta, and y equals r times the sine of theta, to identify an x and y coordinate. My x coordinate is going to be 4 times the cosine of 3 pi over 4, and my y coordinate would be 4 times the sine of 3 pi over 4. So here I'm dealing with 4 times negative root 2 over 2, and this is 4 times positive root 2 over 2. So I actually end up with the x-coordinate negative 2 radical 2, 2 radical 2. And of course, it makes sense that x should be negative because I should be in the second quadrant because my angle is 3 pi over 4. So I can find that I can go quickly back and forth between polar coordinates and Cartesian coordinates, or xy coordinates, by using these identities that we talked about back in our previous lesson. One of the other things that we need to do, though, is we need to talk about this from the concept of polar functions, because when we're dealing with these, remember that r is usually a function of theta. And so, for example, when I say x, I was really saying r times the cosine of theta, and y was r times the sine of theta. So I'm coming up with functions of theta. Theta is usually my independent variable. In other words, I'm usually determining my angle and then calculating what r is for a particular point. So if I wanted to go about graphing a function, let's say I wanted to graph y or r equals cosine of theta. When I'm looking at this, I need to look at it, but I need to look at it from the context of theta being my independent variable, and r of theta being my dependent variable. So if theta is 0 radians, then the cosine of 0 is 1, and that's this point here, 1 unit away from the origin. At pi over 4, the cosine is going to be radical 2 over 2, which is really 0.7071. So that means out of this 45-degree angle, I'm not going to go a full unit. I'm only going to go part of the unit out. And at pi over 2, the cosine is 0. So what happens is now I'm back at 0 when theta equals pi over 2. I am 0 units away from the pole. At 3 pi over 4, which is at this angle here, I'm actually going to get negative root 2 over 2, which means my line, my point actually gets reflected down here. And when my theta is pi, cosine of pi is negative 1, which means when I'm on the negative x-axis, I get reflected here. So what actually happens when I graph this is I find out that this traces a circle with diameter 1. But the period of cosine is supposed to be 2 pi. And what I find is that when I do 5 pi over 4, my cosine ends up being negative root 2 over 2. So for this angle, I actually get reflected back to this point. And so what happens is this graph ends up tracing itself twice. Once from 0 to pi, and another time from pi to pi over 2. And if I complete this table, I'll see that at 3 pi over 2, I end up with 0, which means when I'm on this y-axis, my coordinate is back at 0. At 7 pi over 4, now I'm in this fourth quadrant, but along this line, I'm root 2 over 2 away. So I'm overlapping this point again. And then when I'm at 2 pi, I'm back at the x-axis, and my y-coordinate is back to being 1. So I notice that when I'm graphing r equals cosine theta, I end up with a circle, but it's actually traced twice. And if I do the same thing for r equals sine theta, I'll notice the exact same situation. What's different is because the sine of 0 is 0 at pi, at 0, my radius is 0. And I end up tracing the circle this way, coming back up to y equals 1. When theta equals pi over 2. And then coming back for this full solution back here, when theta equals pi, I'm back at a radius of 0. And for negative angles in the third and fourth quadrant, sine is negative, so I end up reflecting back to these points on the circle. And for pi to 2 pi, I end up retracing these circles. And this is something that I actually notice with a lot of polar graphs, is that a lot of polar graphs, most in fact, most of my circles are going to retrace from pi to 2 pi. They retrace our graphs. So what I really want to do is I kind of want to identify these polar graphs that we talked about back in our pre-calculus class. were several polar graphs that we dealt with. What's notable, and I'm going to divide my list in half, are the ones that deal with sine and the ones that deal with cosine. So here are my cosine graphs that I'm going to put here. The ones that involve cosine and the ones that involve sine. And so the first ones that I want to talk about are our circles. In other words, our graphs that are in the form of r equals a cosine theta, or r equals a sine theta. And the graph of r equals a cosine theta will look like a circle, but it's going to be on the x-axis. And it's going to have a diameter equal to whatever a is. For r equals a sine theta, I'm also going to have a circle, but here my circle is going to be on the y-axis. And that relationship seems sound because we know that cosine is what we're using to determine our x-coordinate. And so what we end up having is x-axis symmetry. In other words, my x-axis will act as a line of symmetry. And for my sine functions, I'm going to notice that I have y-axis symmetry. In other words, my y-axis is acting as my line of symmetry. But we have some other graphs as well. We have the graphs where we're dealing with r equals a times the cosine of b theta, or r equals a times the sine of b theta. And these are our roses, or our flowers. And they have some special behavior. The thing is, I know that cosine of theta is 1, so all of my flowers are going to start here on the positive x-axis. But I know that sine of theta is 0, so all of my flowers in the form of sine start at the origin. So if I was to have something like 2 times the cosine of 3 theta, then I'm going to trace this out three petals, and each of these petals are going to be symmetric with regards to each other. In other words, the axes here are at theta equals 0, theta equals 2 pi over 3, and theta equals 4 pi over 3. For sine, I'm going to be starting at the origin, but I'm going to see this tracing here. And so I notice my line of symmetry here, this y-axis axis, my line of symmetry at pi over 2. But I'm also going to have the symmetric here and here. These are also at 120 degrees because of the way this pedal is. So this is going to end up being at 210 degrees is 7 pi over 6. And this is going to be at 11 pi over 6. So I see these symmetry here, but keep in mind that I'm going to have an odd number of pedals. If B is odd. But what really is interesting is what happens when I'm dealing with an even number of pedals. The thing is, if I was dealing with 2 times the cosine of 4 theta, or 2 times the sine of 4 theta, what actually happens is, because of this symmetry, I'm going to see this come out. I'm going to get 4 pedals here. Let me redraw that. That's not correct. This actually starts at the x-axis. It comes down here, and I'll actually end up seeing that I end up getting 8 pedals. I'll end up getting 2B pedals if B is odd. I mean, if B is even. And I'm going to see the same thing for sine, but it's going to have the y-axis symmetry. So I'm going to end up with 8 pedals for 4 theta. And of course, each of these pedals are going to be at pi over 4 units away from each other. Now, the length of all of these pedals are determined by the lead coefficient, because that's as far away from the origin as I can get. So my lead coefficient is 2. And there's one other type of graph that we really need to be aware of, and that type of graph is our limesons. And our limesons are going to be of the form A plus B cosine theta, or A plus B sine theta. And there are 3 different forms that we have. First, if we end up with A being less than B, we have what we call a looped limeson. So for A equals, for a equals 2 and b equals 4, if I have something like 2 plus 4 cosine theta, I'm going to start here at 6 units away. But as I go through, I'm going to hit the origin and then come out with the loop that's going to be 4 minus 2, or 2 units away. And then I come back around. Notice again, because I'm dealing with cosine, and I've got that x-axis symmetry. But if I have 2 plus 4 sine theta, again, because it's sine, and sine of 0 is 0, I'm going to start at the origin. But I'm going to come out and make my big loop. My big loop, which will be 6 units out, 2 plus 4. And then I'll come back through at pi and then make my other loop here. 4 minus 2, or 2 units long. So if A is less than B, then I end up with a looped limison. If A is equal to B, then we end up with what we call a cardioid, or heart-shaped graph. And so what I see for this situation, if I was to have something like 2 plus 2 cosine theta, is that I'm going to start out at 2 plus 2, which is 4. But my graph actually ends up coming to here, because for the loop part, my loop, it's 0. Because 2 minus 2 is 0. And so I then just continue on for the remainder of this curve. Notice that I've got this x-axis symmetry for cosine. And again, for 2 plus 2 sine theta, I'm going to start not at the origin, but I'm actually going to start 2 units away, because that's my constant term. And so I'm going to see this come up across, and then down under, to fill out the dimple in this cardioid. For A is greater than B, we have what's called a dimpled cardioid. Dimpled limison, I mean. So in other words, my limison is still going to start at this axis, but it's going to come in and really just kind of make a small entrance here. Not actually making it back to the origin. If I was to have something like 4 plus 2 cosine theta, this distance here is 4, but this distance from the origin to here is going to be 4 minus 2, or 2 units away. In reality, it's 2 minus 4, or negative 2 units in this direction, which gets reflected backwards. And I'm going see the exact same thing when I'm dealing with 4 plus 2 sine theta. I'm going to start 2 units away, and I'm going to be going around and then just making a slight indentation there. So these are our limicons. Now, the reason that we're making these big points about these polar graphs is because the main focus of it in our calculus is to find the area of polar curves. And so when we're finding the area of polar curves, what's important to realize is it's not like it was for Riemann sums. For Riemann sums, we're talking about dealing with some function of x, and if we're integrating f of x delta x, we were actually thinking of these being little rectangles that we're adding up. But for polar curves, because my curve is going out to a point, and then as theta increases, I'm going out to a different point. This actually ends up being a sliver of a circle. And so it ends up being 1/2 r squared d theta when I actually want to integrate this. The 1/2 r squared comes from the portion of a circle that we're talking about, and our difference here is the change in theta. So the area of a polar curve is going to be given by the integral from some angle alpha to some other angle beta of 1/2 my function squared d theta. And so when I'm doing these, there's really two key trig identities that I need to remember. One is, they're both the half angle formula trig identities. So in other words, the idea that cosine squared theta is equal to 1 plus the cosine of 2 theta all over 2, and sine squared theta equals 1 minus the cosine of 2 theta all over 2. And I need to know these trig identities because since I'm going to be squaring something that involves sine and cosine, I'll need to find some way to kind of reduce the degree of that. So my quadratic cosine and my quadratic sine become linear in sine and linear in cosine. Or actually just linear in cosine. So I want to do a couple of examples here. I want to start off first with a limicon. So I've got r equals 4 plus 4 cosine theta. So for this limison, this is actually a cardioid because these values are the same, but we actually trace the whole function from 0 to 2 pi. So my area is going to be equal to the integral from 0 to 2 pi of 1/2 4 plus 4 cosine theta squared d theta. And in order to do this integral, I'm going to have to expand this. So I'm going to take the 1/2 out. And expanding this, I end up with 16 plus 8 plus 16 32. Let's try that. 16 plus 32 cosine theta plus 16 cosine squared theta d theta. And now for this integral, I can distribute the 1/2, but I actually want to take care of this cosine squared first. So I'm going to end up with 1/2 times the integral from 0 to 2 pi of 16 plus 32 cosine theta plus, this is going to be 16 times 1 plus cosine 2 theta over 2. And I'm going to be integrating that with respect to theta. So now when I try and amplify this, trying to eliminate some of these terms, I'm going to have 1/2. Let's get rid of that 1/2. Let's distribute it. So I'm going to have 8 plus 16 cosine theta plus, and 16 and a half here is 8, and the half that I'm distributing is 4 times this quantity. So this is really 4 plus 4 cosine 2 theta. And I'm going to be integrating that d theta. So 8 plus 4 is 12. So when I integrate that, I'm going to get 12 theta plus integrating 16 cosine theta is going to give me 16 sine theta plus integrating 4 cosine 2 theta actually gets me 2 sine 2 theta because of use substitution here. And I want to evaluate this from 0 to 2 pi, and sine is periodic. So sine of 0 is 0, sine of 2 pi is 0. So these terms really won't contribute to my area. What will contribute, though, is this 12 theta, because 12 times 2 pi minus 12 times 0 gives me 24 pi, and this ends up being the area of this cardioid. So I want to do one more example of this. And so I want to deal with this from using symmetry, because a lot of our graphs have symmetry when I'm dealing with them. So if I want to take a look at 4 times the cosine of 3 theta, this is our flower, this is a rose, and because I'm dealing with cosine, I'm starting here. So I'm going to have 3 petals. But one of the things that I notice is that if I found the area of this petal, I could just multiply that times 6, because multiplying it by 2 would give me this petal, and then multiplying that result times 3 would get me the other 2 petals. So I know that I'm always starting here at theta equals 0. And I also know that this is going to be equal to 0. In other words, my radius is going to be equal to 0 when 3 theta equals pi over 2, or when theta equals pi over 6. That's going to be this point here for the first flower. So my area is going to be 6 times the integral from 0 to pi over 6 of 1/2 r squared d theta. And again, I can do some simplifying. This is really going to be 3 times the integral from 0 to pi over 6. And this, because it's squared, this is really 16 times cosine squared 3 theta d theta. So this is really 48 times the integral from 0 to pi over 6 of cosine squared 3 theta. And we talked about the trig identity on the previous page. We know that cosine squared of whatever angle I'm dealing with is going to be 1 plus the cosine of twice that angle over 2. So this integral actually becomes 48 times the integral from 0 to pi over 6 of 1 plus the cosine of 6 theta over 2 d theta. So this is what I actually want to go about and integrate. So bringing out the 1/2, I've got 24 times the integral from 0 to pi over 6 of 1 plus cosine 6 theta d theta. And integrating 1 gives me theta, so I've got 24 theta. Integrating this gives me sine of 6 theta over 6. So this actually ends up being 4 sine 6 theta. And I need to evaluate this from 0 to pi over 6. Now when I substitute, pi over 6 times 24 gives me 4. But pi over 6 times 6 gives me pi, and sine of pi is 0. And substituting 0 into both of these gives me 0. So my area actually ends up being 4 pi. So I have to use a slightly different formula to find area, and that's just because of the nature of polar curves. The fact that polar curves come out from the pole, from the origin, rather than having a width and a height. So I have to use the formulas from geometry that we dealt with sectors of a circle, rather than finding the formulas from geometry that we had for finding areas of rectangles. That's the main difference when we're dealing with polar areas. So once again, this is Mr. Potter. Thank you for watching. Have a great day.